So, good afternoon and welcome back to the lecture session. The last time we had discussed about the interpolation, what is all about the interpolation, and we had started with the most fundamental type, that is the point-to-point interpolation, which is usually used in case of drilling machine. Today we will discuss about the linear or straight line interpolation, which is extremely popular and quite often confronted in our machine tool during operation, because majority of our mechanical components having the geometry that can be represented by straight line. But this linear interpolation is exclusively applicable when there is a coordinated motion between the two different axes, maybe xy or it may be xz in case of turning center. So what is the mathematics behind the linear interpolation, how it is implemented in the digital circuit, and associated numerical problem we will discuss at the end. So the content wise, linear interpolation and summation formula, determination of components of fit and pulse frequency, and finally we will conclude by solve problem. Straight line interpolation is popularly known as linear interpolation. The tool movement is not paraxial. In our second lecture, we had discussed in relation to the classification based on the positioning system. One of the continuous movement falls under the basic category, which is known as paraxial. The very name implies paraxial. That means the tool movement is parallel to any one of the axes, either parallel to x or y or z. That means there is no coordinated motion. When the motion is parallel to any one of the axes, in that case, the question or the concept of interpolation is as such not required, because it is very straightforward. There is no combinatorial motion between the any two axes. Okay, so leave aside that part. Otherwise, say for instance, the very good example would be a taper turning or a chamfering. So whenever we undertake a taper turning or chamfering in a turning center, it is a combinatorial motion between the x-axis and z-axis. Similarly, in case of whenever we undertake a milling operation on a plate, if you apply an well-shaped item and apply a triangular cut, then we ought to have implement or execute interpolation following the straight line interpolation in the xy plane. So that is why I have clearly written it is a coordinated movement between x and y in case of milling axis, or x and z axis in case of turning to obtain the desired trajectory. At the very beginning, you should be cautious. Actually, there is no drive system present in the machine that can exactly guide the tool along the desired path, because that inclination of this inclined straight line, it may have any inclination whichever is possible to execute, but there is actually no drive system which guides the tool to follow that particular trajectory. Maybe inclination is 30 degree with the horizontal or 20 degree with the horizontal. So it is not, or it is never possible to guide the tool exactly along the 30 degree or 20 degree inclination. As an alternative, how it is possible to implement? It is a resultant motion between x and z axis if it is a turning center, and if it is milling, then it is a resultant motion along x and y. So that is what exactly it is written. In essence, CNC machine tool utilize two separate closed loop control system, one along x axis and another along y axis, that is for milling, and similarly one along x axis and another along z axis for turning machine. So obviously there will be some small error present in the geometry that is obtained, but that level of error is extremely small, and the accuracy which is obtained, that is quite significantly good, which makes it amenable for mechanical applications of that particular component. So the key features of the movement along the desired path is therefore accomplished by a resultant motion obtained from two orthogonal movements along x and y or x and z. During linear interpolation, the control system will accurately and automatically calculate a series of very small incremental points along the two mutual perpendicular axes separately. That is what exactly the role of the function of interpolation. I am repeating, the control system will accurately and automatically calculate a series of very small incremental points along the two mutually perpendicular axes separately. That is, for x axis separate, y axis separate, or if it is a combination of x, z, then separately for x as well as for z. So this work or activity exactly implements the basic philosophy of interpolation. Given the two extreme points, the responsibility is to calculate the intermediate points, of course very closely spaced, so that our desired trajectory can be obtained by resultant motion of the two different axes, so as to yield a resultant desired path that guides the tool as close as possible to the programmed linear path. Once again, strictly speaking, the actual tool path can never be a continuous one along the desired path, rather it is an approximation to it. But it appears that the machine is executing a perfectly straight line motion along the programmed path, because the deviation of the error associated with this approximation is so small that it can be ignored, and the path is just sufficiently good enough, or the accuracy is good enough for its mechanical applications. To understand the mathematics, how to develop the formula and how it is implemented in the electronic circuit, particularly the digital electronic circuit, let us come to this or refer to this particular drawing. Just simply the way we develop our equation of a straight line in our coordinate geometry system, that what exactly is taken care of. So the tool is supposed to move from the point P1 having coordinate x1, y1 to reach to the point P2 having coordinate x2, y2, and the inclination of the P1, P2 line with x-axis is say phi. We have considered an intermediate point P having coordinate xy that lies on the P1, P2. So the point P divide the entire line into the two segments. One is P1P, another is P2. Okay, so with reference to this particular drawing, if you consider that this phi angle, okay, then cos phi will be how much? X minus x1 by P1P. I am going back to the particular drawing. So if you take the projection, what is this incremental horizontal movement? It is x2 minus x1. So if we take cos phi, so cos phi will be how much? X2 minus x1 by entire P1 and P2. That is what exactly is written over here. X minus x1 by P1P, and that can also be represented as x2 minus x1 by P1 P2. Just using the relationship of similar triangle. Once again, this cos phi can be written as x minus x1 by P1P, and that is also equal to x2 minus x1 by P1 P2. Very simple mathematics. Now if you just rearrange, you will find x equal to x1 plus P1P by P1 P2 into x2 minus x1, and finally it can be modified and can be represented like a summation formula. Now for this purpose, to understand how we achieve this particular relationship, we need to go for a little bit of more work. It is not at all complicated. Objective is that now the question may arise in your mind, the cos phi given the angle phi, it is not at all difficult task to calculate what will be the value of cos phi. But the thing is that it is not for pure mathematics. We have to consider how this mathematics can be implemented in the digital electronic circuit so that motion can be executed. That is our objective. So this is the reason for which it requires some sort of modifications. So we can, from this particular relation, I am carry forwarding this particular expression, x equal to x1 plus P1P by P1 P2 into x2 minus x1. X equal to x1 plus, better to write like this, x1, x equal to x1 plus P1P plus P1P by P1 P2 into x2 minus x1. So P1P is the distance along that particular path, incremental, and P1 P2 is the total length of the straight line segment, that is P1 to P2. Now thing is that eventually it is expected that tool will have a definite velocity along the same path. So this distance, in the absence of any acceleration or deceleration, it can be represented as v multiplied by t. For the time being, I am omitting the t part. Similarly for P1 P2, velocity remains same. Now come, just consider that P is not a static point. P keeps on changing dynamically in real time. Its starting point is P1 and eventually the P will reach to the destination P2 as far as x-axis movement is concerned. Now one pulse will be emitted to cause some incremental distance along x-axis. So if that is so, let us consider delta t is the time required for the one pulse so that some incremental movement takes place while moving from P1 to P. Once again I am reiterating that P is a dynamically changing point. So first it starts from P1, then for one incremental pulse which spans over delta t time, it moves to the point P. So the distance coverage will be P1P. So we can write it velocity into time. Similarly for P1P is the longer distance. So since more number of pulses required to cover the entire distance, and these pulses are always in the integer type. So if we consider that n number of pulses are required to cover the entire distance along the P1, P2, of course as far as only x component is concerned. So we can say that n number of such pulses will be sufficient to cover this particular distance. So it will be multiplied by n of delta t. For one pulse, time consumption is delta t. So for n number of pulse, simply it will be n delta t. Now x2 minus x1 part remains same. So v remains, cancels out, delta t cancels out. So eventually it becomes x1 plus x2 minus x1 by n. So this implies that if n number of total pulses are required to cover the entire distance, then for one incremental pulse, the corresponding x position will be initial x1 plus x2 minus x1 by n. That is this portion is the incremental part of the displacement along x-axis corresponds to one pulse. So if the second pulse is emitted, then what will be the distance covered up? So this portion multiplied by 2, for third pulse multiplied by 3. So when n number of such pulses will be emitted, this will be simply multiplied by n. So if I multiply this with the n, the tool is supposed to reach to the destination point x coordinate, that is x2, because if I multiply by n cancels out, plus x1 minus x1 cancels out, and finally we will reach to the x will assume the value of x2. So incrementally we have to add the incremental value with the current value to get the next value, and this will continue unless and until the final destination point x2 is achieved. So to facilitate its implementation in the digital circuit, it is expressed in this way. Sorry. So x2 minus x1 over nu varies from 1 to n. That means n number of iterations are required. Every time x2 minus x1 by n amount corresponds to one pulse is added to the previous value. to get the new value. So as the series of pulse train is emitted, that tool will keep on moving incrementally every time by the amount x2 minus x1 by n, and when n number of pulses will be emitted, it will reach the final destination of x2. Okay, so just to facilitate implementation of the above formula in digital circuit, it is the previous expression is expressed like this way. One thing also you should remember that this trigonometrical function, that is cos phi, sin phi, tan phi, these cannot be implemented in electronic digital circuit. Okay, that is why this sort of modifications are required, so that with the incremental pulse, what will be the incremental movement. Same logic holds true in case of y-axis. Same thing, only x are replaced by the y and you will get the same expression. So these expression for x-axis and expression for y-axis together is called summation formula for the linear interpolation in NC-CNC system. Just for illustration, so nu is the number of iteration. So initially x I have taken, because x and y or x and z, it is every time it has to be separated one. So just pick up any particular axis. Say for instance I have taken x axis. So for one in x axis as such horizontal axis we have considered nu, and in the vertical axis we have considered x. So when it is 0, that means at the starting point at the beginning, it will assume the value of x1. So when nu assume the value of 1, that means for one incremental pulse, okay, the corresponding movement of the tool along x-axis will be this much additional. For second, additional this much, all are equal because it is x2 minus x1 by n. So that is why shown, if you take the, what is the vertical incremental value, it will be always x2 minus x1 by n. And when n such pulses will be emitted, it will reach to the final destination point along the x-axis, that is the x2. So this is what exactly is called staircase effect. That means this staircase effect will be present in the job of the component that we machine for x as well as for z or for y-axis. But this amount is extremely small and won't harm the accuracy of the component that we produce. Okay. So that is the summation formula which is used by the data processing unit, so that the tool can be navigated in space following the definite trajectory while moving from point P1 to the destination point P2. Now the second part is the determination of the pulse frequency corresponds to a given feed rate. Unlike PTP interpolation, the travel time in linear interpolation along two orthogonal axes is same, and the motion along two axes is terminated simultaneously. This is very important point and the distinguishing feature as compared to the PTP. In PTP, the motion was not coordinated. So depending on the incremental value of delta x or delta y, the distance which is the lower one, so motion along that particular direction will be completed earlier than the other one. Because incremental displacement is different, velocity for both axes is the same and the highest. So definitely time will differ. But in this case, since it is a synchronized motion, so the motion along xy or xz should continue in a coordinated fashion and it will terminate simultaneously. So according to the magnitude of the displacement along x and y or x and z, the velocity has to be adjusted. Here velocity means the feed velocity, that is the component of the feed along two mutually orthogonal axis system. So that is what exactly is taken care of. In the previous case, in case of PTP, time for x and time for y was not same. But in this case, time, since it is a coordinated motion, time will be same. So that is why I have written t equal to x2 minus x1 by fx. That is equal to y2 minus y1 by fy. That is equal to L by f, which is fx equal to x2 minus x1 by, if we rearrange, you will get fx equal to x2 minus x1 by L dot f, and fy equal to y2 minus y1 by L dot f. For better understanding and for ease of distinguishing between the what is called PTP and straight line motion, very simple to remember in one. In this side I take PTP and this side I take straight line. The basic requirement is very simple, that is we will obey, or the system will obey S equal to Vp, that is applicable in CNC. S equal to Vt, that is displacement equal to velocity into time. What we had assumed, or what it is considered in case of PTP, Vx equal to Vy is common, that is V common, and that is the V max. If that is so, Tx will be delta x by V common, and Ty will be equal to delta y by V common. So unless and until delta x and delta y equals, definitely Tx won't be equal to Ty. So velocities are common and maximum to reduce the time. So Tx won't be equal to Ty. The problem that we had solved, which was set in 2020 GATE problem, time for Tx was 0.5 minute, if you can recall, and for Ty it was 0.75. So their motions are not synchronized. So in contrast, if you come to the straight line, since the time is same, velocity has to differ. So for suppose this is our given straight line having the length L, and in the numerical problem it is expected that tool should follow a particular feed rate, that is the velocity of f. But as we had discussed, there is no possibility of applying motion along that particular desired trajectory. So this f means basically feed rate. So just like your basic vector, if we identify this as a fr, so it can have two components, one is fx, another is fy. But in this case, since time is same, since time remains same, so we can write T equal to delta x by fx equal to delta y by fy, that will be equal to L by f. L by f, that is desirable according to this particular trajectory. But eventually we have to implement the motion along two orthogonal axis movement effective through x and y or xz. So for x, delta x by fx is the time, that will be equal to delta y by fy, and which will be also equal to length by f. So that is how it is very easy to understand and distinguish between the point to point and straight line. Here velocity is common, time differs. Here time is common, velocity differs. Velocity means nothing but fx and fy, that is the two orthogonal components of the given or desired feed rate. Okay. So this is what we had already discussed. So if we just go for interchange, you will get fx. So in a numerical problem, f will be given, either L can be given or x1, x2, y1, y2, that is the two coordinates can be given, and from which we can easily calculate what is fx and what is Fy. So once Fx and Fy is known, we can also represent it what will be the pulse frequency, because one pulse will cause x2 minus x1 by n amount of incremental movement. So if Fpx is the pulse frequency for x-axis, simply if we multiply by it, so that is the movement in a per unit time, because frequency is expressed in number of pulses per second, that is the hertz. So incremental distance is x2 minus x1 by n in millimeter. So eventually what will get? Fx, that is the feed rate in along x-axis. Similarly, Fy will have y2 minus y1 by n dot Fpy. Usually Fpx and Fpy becomes a common value of F. If that is so, then you can easily calculate what will be the value of a common Fp by squaring and adding these two equations. Just to limit the number of slides, I have not undertaken that one. But one thing you should be careful, what would be the least amount of the value or incremental value along x and along y? That is nothing but the basic length unit which we had discussed earlier. Any movement below or less than BLU is not possible. So that is why x2 minus x1 by n should be always greater than equal to BLU. And usually BLU for x and y axis also becomes same. If that is so, then so n or the BLU defines what should be the number of iterations, that is the what should be the value of n into which the total number of steps would be considered for covering the distance from P1 to P2. Okay. So the formula that we had developed earlier, that is popularly known as summation formula. In case of PTP, it was activated in a programming by a preparatory code G00. Similarly, if you want to implement in straight line or linear interpolation, the corresponding command will be G01. Okay, you have to remember all these things while discussing the CNC programming. And one thing you should remember, keep in mind, this interpolation is implemented in a digital differential algorithm in a digital electronics system. Okay. So just one illustrative problem. A DC servo motor drives the x-axis of a NC milling machine table. The motor is coupled directly to the table lead screw. The motor is coupled directly to the table lead screw. That means there is no gear. That means RG equal to 1. So that you have to understand from the problem statement. And the screw pitch is 6.25 millimeter. An optical encoder is connected to the lead screw. The encoder emits 125 pulses per revolution. To execute a certain program instruction, the table must move from point, that is the starting point, that is the P1, having XY values are 87.5 and 35.0 respectively, and the end point or the your desired target point X25 and Y 180 millimeter in a straight line trajectory at a feed rate of 200 millimeter per minute. This 200 millimeter per minute is the desired feed rate along that particular path. But while calculation, we have to resolve into two components, Fx and Fy, the way we have discussed right now. So determine the control resolution of the system for the x-axis, rotational speed of the motor and frequency of the pulse train emitted by the optical encoder for that desired feed rate. Solution is also not very difficult. Pitch is, what are the data given? Pitch, encoder emits 125 pulses per revolution. So given the two extreme points, what is the incremental movement along x? 25 minus 87.5 minus 62.5. This minus has got nothing to do with this your numerical problem. Only it signifies the movement will be along the z axis. Sorry, negative direction. For y it is 180 minus 35 equal to 145 millimeter. Feed rate given 200 millimeter per minute. So the length of the trajectory, just you take under root of the square of 62.5 and 145. So it will yield 158 millimeter. So the control resolution of the system for the x-axis will be 6.25 by 125 millimeter, that is 0.05 millimeter, because lead screw pitch is given 6.25 millimeter and the positional displacement is monitored by the encoder having 125 pulses per revolution. So for one pulse, what would be the distance that can be measured? 6.25 by 125, that yields 0.05 millimeter. And the way we had deduced for linear interpolation, that is delta x by fx equal to delta y by fy equal to L by f. So that is what exactly is used in case of x-axis to obtain fx, which yields as a 79.11 millimeter per minute. Rotational speed of the lead screw will be 79.11 by 6.25. That is the RPM, because the transverse displacement is fx is 79.11, this much millimeter per minute. That is a linear. So if we divide it by the corresponding pitch, we will get the rotational value, which yields 12.65 RPM. And since the lead screw is connected directly to the motor, there is no gear ratio Rg equal to 1. So the rotational speed of the lead screw will be the same as that of the speed of the motor. And the frequency of the pulse chain emitted by the optical encoder will be how much? 12.65 is the number of rotation. Encoder disc has 125 number of slots. So what is the total number of pulses emitted per minute? Mind that this is RPM, revolution per minute, but frequency always we ought to express in hertz. So per minute has to be converted to per second. So 12.65 into 125 is the total number of pulses emitted in 1 minute. So if we divide it by 60, we will get 26.35 pulses per second, which is the pulse frequency and expressed in hertz. Okay, so that is all about the straight line interpolation, and I believe that you will be able to distinguish what is the merit of the PTP interpolation and what is the straight line interpolation. In case of PTP, motions are not synchronized, and to reduce the cycle time or the idle time, highest possible common velocity is employed for both the axes. But in case of straight line or linear interpolation, the coordinated motion calls for simultaneous termination of the motion along both the axes. So that implies the velocity has to differ, so that the tool reaches the end point entirely following the coordinated motion along the two orthogonal axis movement, either xy or xz. Okay, so thank you very much for your patience hearing. In the next class, we will discuss the last part, that is the circular interpolation, in the same manner. Okay, thank you once again.